Their nature on a rampage. To be in their path is to be in the scariest place on Earth. The size and intensity of hurricanes make them the most feared and destructive of all storms. How do they start? How do we track them? Can we stop them?
We're about to fly into the eye of Hurricane Wilma on bottom.
A swirling mass of clouds, ferocious winds, lightning, raging seas, torrential floods. Hurricanes are the ultimate in extreme weather.
In a typical strong hurricane, the energy budget of that hurricane releases on the order of tens of thousands of Hiroshima-sized nuclear weapons per second.
Traveling for hundreds of miles, and with potential wind speeds of over 200 miles per hour, they are capable of bringing nations to their knees. Those who follow and study them think of hurricanes almost as living, breathing entities.
Every storm has a different personality, and size matters. We have to know whether a storm is broad and destructive or very small and intense.
They're capable of the virtual destruction of cities. On August 29, 2005, Hurricane Katrina triggered one of the worst natural disasters in the history of the United States. The tragedy left in the wake of this storm makes it more important than ever that scientists unlock the secrets of these destructive giants. Some of that learning starts here, with Hunter planes. These flying laboratories travel right through a hurricane and are equipped to collect information about the storm from the inside out. October 21st, 2005. This WC-130J is part of the Air Force Reserve's Weather Reconnaissance Squadron. It will fly into Hurricane Wilma, a storm that's already registering some record numbers.
The central pressure in Wilma was the lowest central pressure of a hurricane ever measured in the Atlantic Basin. Quite simply, that's a very intense hurricane. The lower the pressure, the higher the winds are going to be in the storm.
The plane will fly some 900 miles from Dobbins Air Force Base in Georgia to where Wilma is currently raging, between the Yucatan Peninsula of Mexico and Cuba. The experienced crew members expect a bumpy ride, with the hurricane's ferocious winds initiating huge fluctuations in altitude.
The amount of altitude that you actually lose as you penetrate through the hurricane is dependent upon the severity or how intense the storm is. But sometimes you can have as much as 2,500 and maybe a 3,000-foot loss in altitude as you penetrate the eye wall of the hurricane.
And every flight into every storm is different. Some are smooth, some are extremely rough.
The plane is racing the clock because scientists at the National Hurricane Center in Miami, Florida, want its data while the storm is still out at sea.
We're going to catch it right before it goes on shore, and it's vital that we get our readings to them right before the hurricane does get on shore, because that way they'll know exactly what it's doing as it's landfalling.
The plane will enter the storm at an angle calculated to give it the smoothest ride.
Depending on what the wind speeds are when we're in the storm, depends on how we're going to go into it. The airplane's going to weather vane into the wind, and that's the way we're going to stay on a track directly to the center of the storm. If we just went straight towards the eye of the storm without crabbing into the wind, as what we call it, we would just pretty much get blown around the storm by the winds, especially with 150-mile-an-hour winds is what they're calling right now.
Their main target is the eye of the storm, where the most important readings must be taken.
We want to go to the eye because we want to mark not only movement but pressure, because the pressure is dropping, then they know it's intensifying. If the pressure is coming back up, then they know it's probably weakening.
A flight meteorologist is in charge of collecting the data.
This particular console collects the horizontal data as we fly along. That is, we're measuring temperature, pressure, humidity, wind speed, and direction at a very rapid rate, typically 1 sample per second.
Besides collecting information from instruments on board the plane, the crew also utilizes devices called dropsondes, which are released beneath the plane and fall by parachute down into the sea.
The dropsonde is a cylinder 3 inches in diameter by 18 inches long, weighs just over a pound. It falls at 2,500 feet per minute. Radios back pressure, temperature, relative humidity, and winds twice per second from flight level down to surface. From this, we get the pressure on the center of the storm, the winds all the way down to the surface for the National Hurricane Center to improve the forecast.
With the data collected, they plot a course to return to the United States. They have crisscrossed the storm 6 times without incident or major turbulence. The flight ends safely. For the crew, this mission is more than just a job. Living with, studying, and even having their own families hit by hurricanes, they know firsthand the destruction that the giant storms can cause.
Obviously, most of us were affected by Katrina and have been affected by other storms. And to a person in the whole unit, we cannot stand to see the landfalling hurricane, the devastation it causes.
The idea for flying airplanes into hurricanes to collect meteorological data was born during World War II.
The person who's given credit, and rightly so, for being the first person to deliberately fly into a hurricane was Colonel Joseph Duckworth. Duckworth invented a system of training pilots how to fly when the clouds are all around you. And one day in 1943, a hurricane was approaching the Texas coast. And Duckworth took another pilot with him, and they flew into a hurricane, flew around for a while, flew back, landed safely. The base weather officer heard about that, and he said, "Hey, I want to go too." They did it again. This time they took some measurements. When the U.S. Weather Bureau heard about some of the measurements they had taken, this prompted them to say, you know, we should really be using airplanes to fly reconnaissance into hurricanes.
In the 6 decades since Duckworth's first flight, every effort has been made to make this hazardous duty as safe as possible. Today, meteorologists are even using an unmanned aircraft called the Aerosonde to fly into areas of hurricanes that are too treacherous for traditional planes.
The Aerosonde is about 6 feet long with a wingspan of also about 6 feet, and it has a small gasoline-powered engine which is able to operate for up to 24 hours per flight. The Aerosonde is launched via truck, which rolls down the runway at a fixed speed of 55 miles an hour.
It's a remote-controlled aircraft.
It is steered through commands via GPS tracking, and its location is relayed back to the pilot.
Although it will never replace traditional chaser planes that can carry many more instruments, the Aerosonde is vital for getting right down to the surface of the ocean to make readings. This is an area that a larger plane can't fly to safely.
The area close to the water in hurricanes is important to measure because much of the energy exchange between hurricanes and the underlying sea surface occurs in these extremely high wind conditions near the eye wall of storms.
These monstrous windstorms are known by different names throughout the world. In the Northwest Pacific Ocean, they're called typhoons. In Australia and the Indian Ocean, they're known as tropical cyclones. In the North Atlantic Ocean, the Caribbean Sea, the Gulf of Mexico, and the Northeast Pacific Ocean, they're called hurricanes. But just what is a hurricane? The Atlantic hurricane season starts when summer arrives, and the water off the West African coast begins to warm up.
The important thing about hurricanes is they live on the heat energy stored in the ocean. All summer, the sun shines on the tropical sea, and the water gets to be as warm as bathwater, basically. When the hurricane starts, the wind blowing over the water causes evaporation. The water vapor goes from the sea into the atmosphere, taking the heat that it needs to evaporate from the ocean.
As the column of moist, warm air rises, condensation occurs. This is the process by which water vapor turns into droplets of water, and heat is released. The heat warms the air column, and the water drops create clouds, which develop into rain and thunderstorms. These thunderstorms are the basic building blocks of hurricanes. The storm system begins to operate as a huge heat engine, pulling in warm, humid air near the ocean's surface. and spitting out cooler, drier air into the upper atmosphere. The system's strong winds are caused by air rushing in from below to replace the air rising in the storm.
It was kind of like a chain reaction. You got more and more air rising, more humid air coming in to replace it.
Interaction between the motion of the air and the rotation of the Earth causes the storm to spin. This is known as the Coriolis effect. In the northern hemisphere, hurricanes spin in a counterclockwise direction. In the southern hemisphere, they spin clockwise. A column of calm air develops in the center of the system. This is called the eye. It's a nearly cloudless space, filled with light breezes and clear skies. The system's raging winds spiral around the eye. When these winds reach a speed of 74 miles per hour, the storm is officially called a hurricane. Trade winds push the entire system west across the Atlantic. Hurricanes are rated in categories from 1 to 5. A Category 1 being the weakest, and a Category 5 the strongest, with wind velocities of over 156 miles per hour. The storms have been the scourge of mankind since before recorded history. Early native tribes of the Caribbean considered them evil spirits from the sea. The Mayan storm god was called Huracan, and the storm god of native Caribbean islanders was called Huracan. It is believed that the word hurricane derives from these sources.
Columbus was really the first European to run into a hurricane. It was on his second voyage to the New World. He actually encountered a storm. Apparently it wasn't too bad because he survived.
Although weather records are scarce, it appears that storms hit for centuries with about the same regularity as they do today. But scientific knowledge of their origins and makeup was non-existent.
It's hard for us to imagine, but by the early 19th century, people didn't really realize that storms were huge whirlwinds. The picture they had was kind of like, you know, the wind came up, it blew, then it stopped.
In the 1820s, self-taught scientist William Redfield became one of the first to start unlocking the secrets of hurricanes.
He had noticed on a walking trip across Connecticut after a big hurricane hit that trees in one part of the area, they were all blown down facing the northeast. A few miles away, all the trees were blown down facing the southwest. And he started thinking about this, you know, what in the world can make a storm blow down trees this way in one area and not that far away facing the other way. And what he concluded was that large storms, like hurricanes, were really whirlwinds. The winds were going around a center.
The hurricane that hit Galveston, Texas on September 8, 1900, created one of the greatest natural disasters in American history, killing between 6,000 and 8,000 people.
The people who died in Galveston almost universally drowned. The waves from the storm destroyed the first line of houses. The debris from the first line of houses destroyed the second line of houses, and it swept about a third or almost halfway across the city.
During the first part of the 20th century, advances in radio communications, especially from ships at sea, improved our ability to signal early warnings about the storms. World War II gave birth to some major technological advances for studying hurricanes. Besides the development of hurricane hunter planes, it also introduced radar.
The whole idea was to spot enemy airplanes or enemy ships. When people first started experimenting with radar, they would see fuzzy images and things, really caused by the weather. You know, radar sends out a radio wave which scatters or reflects off of things, such as an airplane, but also raindrops or ice and clouds. And it showed that a hurricane is made of spiral bands, you know, bands of thunderstorms that are spiraling in to the eye wall. And before that radar picture, no one really realized that hurricanes had this structure.
Today's meteorologists use Doppler radar.
Nowadays, anyone who watches television weather is going to hear about Doppler radar. When a radar sends a beam out to bounce off of a raindrop, say, if the wind is blowing the raindrop away from the radar, that means a wave coming back is going to have a longer frequency. You can think of it in a way as it's stretching the wave out. If the raindrop is going toward the radar, it's going to squeeze the frequency and give it a higher frequency. What Doppler radar does, basically it's the computer processing of the radar data.
Many radar antennas are housed in domes to protect them from the weather. Doppler radar can present meteorologists with a giant color scheme of the storm.
The light blues represent precipitation, say for instance drizzle. Then when you get into the greens, you start getting into heavier rainfall amounts. Then when you get into the yellows and the oranges and the reds, that's very, very intense precipitation, and that is typically where the strongest winds are located.
Radar has unlocked many hurricane secrets. But in order to get even more accurate readings, some operators are driving Dopplers on wheels right into the eyes of the monsters. The red spot on the planet Jupiter is really the top of a giant spiraling hurricane. The storm is larger than the Earth and has been raging for more than 300 years. Nature Tech Hurricanes will return on Modern Marvels. We now return to Nature Tech Hurricanes on Modern Marvels. Although radar is a technological miracle that has given us a detailed look at the inner workings of hurricanes, it still has some drawbacks.
The farther an object is from a radar, the poorer you are able to see that object. And that's due to both the spreading of the radar beam and the curving of the Earth away from the radar beam. If an object like a hurricane eye is far away from a radar, you can't see details in it because it's too far away and it's too blurry. And you also can't see some of the most important details, those happening near the ground, because the ground is literally over the horizon from the radar.
Are we going to stay put or want me to do a U-turn?
I don't know. It's just getting stronger.
In order to remedy this problem, some intrepid meteorologists are turning to Dopplers on wheels.
The Doppler on wheels are able to drive up into the hurricane, so we can see very, very fine details that are just impossible to see from farther away. We are 100 times closer than a typical land-based radar, and we sample much, much faster. We're getting 10 to 100,000 data points where a conventional radar might just get one.
Scientists are hoping the device will unlock some secrets of hurricane behavior that so far have eluded them.
The prime focus of the Doppler on wheels is to study the variability of the winds in the hurricanes as they come on shore. We know that some neighborhoods experience much more damage than others, and we also have discovered that there is a lot of variability in the wind field. Some areas are getting much stronger winds than others. And what we want to understand is how those winds are related to damage. That's an important gap. Is it 150-mile-an-hour winds for a few seconds, which are the most damaging? Or is it the prolonged effect of 100-mile-an-hour winds?
It's a dangerous task, but operators take every precaution when deploying the vehicle.
We do detailed surveys of our deployment locations so we know that we're not going to be downwind of sources of debris. We don't park near big trees. We don't park in a low area that's going to get flooded. Even though we're right in the middle of the hurricane, in the worst part of the hurricane, we have a perfect safety record because we take these extreme precautions.
Although radar has been an essential tool for hurricane research since World War II, another major advance came with the introduction of weather satellites during the 1960s. For the first time, we were able to see the awesome scale of storms in one picture.
It really does give you the big picture. Where are the fronts? Where are the high pressure centers? Where are the low pressure centers? Where's the hurricane moving?
Satellites provide far more information about hurricanes than simply photographs.
We can see them speed up and slow down. We can check out the temperatures of their cloud tops. We can actually keep track of the sea surface temperatures from satellites.
America's first weather satellite, the TIROS-1, was launched in April 1960. Satellites have given us the ability to have an early warning system for hurricane threats,
To go out more towards the Yucatan.
and thus to save hundreds of thousands of lives.
In the old days, if the hurricane forecasters were lucky, A ship might stumble into a breeding storm and ships would send weather information back. But hurricanes tend to form over parts of the ocean where there aren't too many ships. So the first thing that satellites do is they make sure that a hurricane is never going to sneak up on any part of the world.
The ability of satellites to show scientists whether a storm is growing or diminishing over a period of time is extremely important for weather prediction.
As we see in this Hurricane Katrina animation loop, it starts out with a very small eye, and then 3 days later evolves into a much larger hurricane circulation. Now we're talking about a wind field that's more than 3 times the size as it was when it passed close to Key West, Florida, compared to the time that it made landfall over southeast Louisiana and Mississippi.
Besides satellites and radar, the other major tool in hurricane research is the computer.
Computers have been responsible for really some of the big improvements we've seen in forecast of where a hurricane is going to be. For instance, in 1990, the National Hurricane Center forecast where a hurricane would be 24 hours from now was on the average about 128 miles from where it actually ended up. By 2004, that had been cut pretty much in half, down to 70-mile error.
Billions of pieces of weather data are collected by organizations like the National Center for Atmospheric Research in Boulder, Colorado, and processed through supercomputers to create models that show scientists what the weather is doing and what it's likely to do.
The floor there is about 13,000 square feet. The computer we have right now is an IBM Power 4. It's one of the faster machines anywhere that does forecasting in near real time.
The supercomputers devour data from every source available.
These are the observations from satellites and from radiosondes, weather balloons, and aircraft and buoys and ships on the ocean surface. All of these go in every time, whether there's a hurricane or not. When there's a tropical cyclone, we send out special aircraft with instruments that are dropped into hurricanes or remotely sense the hurricanes, and these can then be assimilated into our models in addition to all of the other data that routinely goes in.
After the information is processed, the resulting computer models are sent to Miami's National Hurricane Center to be evaluated.
We are the final word in terms of the U.S. government. We're responsible for providing the U.S. citizens with tropical cyclone forecasts for all storms throughout the Atlantic and the eastern North Pacific Ocean basins.
One major challenge facing the Hurricane Center is that the computer models of a particular storm are sent to them by weather forecasters from all over the world. And each interprets the numbers a different way.
Say the UK Met, the one by the United Kingdom Meteorological Office, is saying the storm's going to go here. No Gaps, which is a U.S. Navy global model, says it's going to go there.
Forecasting hurricanes is easy, but validating the models, verifying the forecasts is hard.
Often, the Hurricane Center looks at as many as 25 computer models when trying to determine the course a hurricane will take.
You can go back and look at just about every single storm, and you will see that of the 25 or so models, there's always one that seems to do better than the rest of them, but it isn't always the best one in every particular situation. We have 4 computer models that tend to outperform all the other models, and those are the ones that we tend to rely on the most. However, we never key our forecast on any one particular model. We try to look at a consensus to see if the computer models are, headed in the same direction. Of course, the northeast portion.
This consensus approach works well about 85% of the time. But the rest of the time, someone must step in and make a crucial decision.
Reliable thing we've got.
One individual, because of their experience, may have seen a certain situation. They say, well, the models are deficient in this area, and this is why I think the track should go this way, or the intensity should be increased or decreased.
The human factor came into play on October 17th, 2005, when the Hurricane Center had to predict the course of the super hurricane, Wilma.
One of the things that
meteorologist Stacy Stewart overrode the computer models and came up with a more accurate reading of the hurricane's potential path.
This was the forecast track that was issued. There was my day 5 position, and my position was about 240 nautical miles to the northeast of our most reliable forecast tool that we have. 5 days after this was issued, this is where the hurricane actually ended up being. So the forecast track was on. My forecast speed was a little bit fast, but it was still better than our most reliable forecast model.
We may have become more accurate in predicting hurricane behavior, which helps forewarn residents to flee. But we certainly can't control them. Wind damage caused by a giant hurricane can be catastrophic. Yet ironically, it's not the storm's main weapon. Storm surge is its real knockout punch. The National Hurricane Center in Miami, Florida, is built to withstand a Category 5 hurricane. Its reinforced concrete walls are 10 inches thick, and its backup power system can keep the center running for 10 days. Nature Tech Hurricanes will return on Modern Marvels. We now return to Nature Tech Hurricanes on Modern Marvels. Of all the hurricane's weapons, the most feared is storm surge.
As a hurricane is moving across the ocean, the winds are pushing the water ahead of it. When the hurricane is out in deep water, a lot of that water flows away underneath the storm. But as you push the water up on a very shallow coast, there's no place for it to go, so it builds up, comes ashore as a storm surge.
Storm surge is so deadly because many population centers are located along coastlines. In 1970, a storm surge in East Pakistan killed more than 250,000 people. And it was storm surge in the 1900 Galveston hurricane that leveled that city. Scientists have developed computer programs called slosh models that help them predict potential storm surge damage. SLOSH is an acronym for sea, land, and overland surges from hurricanes.
When the storm is actually approaching, you need to know what this storm is likely to do. For instance, how early in the game is it likely to flood a coastal road that people might need to get out on? And the information it uses is the shape of the bottom of the ocean at the place where the storm is coming ashore, the shape of the land, how strong the hurricane is, and the distribution of its wind.
This is SLOSH storm surge forecast model output for the southwest coast of Florida. As Wilma was coming in from the southwest in October of 2005. What people need to understand from this is that these colors represent the height that the ocean surface is forecast to be above sea level from where it normally is going to be. In many of these areas right here, the storm surge forecast is 17 feet. If your house is only 12 feet above sea level, that means you're going to have 5 feet of water in your house. If you can't swim, that means you're probably going to drown.
So these kind of models are used both to help emergency managers make their evacuation plans, and also when the storm is actually occurring, where the worst surge might be, where you might find victims, you know, say on the roofs of buildings.
Storm surge may pack a hurricane's deadliest punch. But when most people think of hurricanes, they think of wind. Conventional buildings have a poor record of survival when battered by hurricane-force winds. Hit by intense gusts, roofs blow off, windows shatter, doors cave in, and entire buildings can be destroyed. Today, some builders are turning to innovative alternative designs when constructing buildings. Take the dome, for example. It's an old idea that's gaining new attention in hurricane country. Unlike conventional structures, domes give wind very little surface space to latch onto.
The shape of a concrete dome is absolutely perfect to withstand wind. There's only a very small area that the wind actually hits straight on. All the rest of it, it hits at an angle and flows around the dome itself.
The only areas of the building that may be vulnerable to wind are the windows. When constructed in hurricane-prone areas, domes should be equipped with strong window louvers to seal them tight. Like the building itself, the construction of a dome requires simplicity, matched with ingenuity.
The way we build a monolithic dome is we start off with an airform. It would remind you of a truck tarp. The fabric we use is actually quite stiff. It has stretch, but it's not like plastic or rubber bands. We have a computer-generated pattern. We put the pattern down on the fabric. We cut it out. It's welded together in the shape of the dome. We pour a concrete ring foundation. We attach the truck tarp to the foundation.
We then take a fan, if you will, we call them inflators, and hook it to the dome and turn it on, and it blows up just like a balloon. And in larger buildings, we have two, primarily for redundancy in case the power goes off. In the case of very large dorms, we may have 4 fans on it, but the majority of our domes are built with 1 fan.
Then we do all our work from inside, which is what's really unique about this kind of construction. We spray the inside surface with 3 inches of polyurethane foam. That's the world's best insulation, and it sets up in 3 to 5 seconds. Then we tie rebar to the underside of the foam. Rebar is reinforcing steel. It's usually bars of steel 3/8 of an inch in diameter to a 1/2 inch. On big domes, it'll be up to 1 inch in diameter. And after the rebar is all tied in place, it looks like a bird cage inside. Then we spray concrete in again up against the urethane, embedding all of that concrete. When that's done, we can turn the fans off and open the doors and windows, and we now have one of the world's strongest structures.
Dome buildings came under scrutiny after Hurricane Katrina slammed into the Louisiana Superdome. While it stood firm, it sustained damage because it wasn't constructed to withstand a hurricane greater than Category 3. Of all the structures built to withstand hurricane force winds, perhaps the most carefully designed are skyscrapers. The skyscraper capital of the world, New York City, is vulnerable to hurricanes. On September 21st, 1938, one passed some 55 miles east of Manhattan. Had it made landfall on the island, many believe it would have caused extensive damage to the huge structures. With winds of more than 100 miles per hour taking aim at their massive walls, giant buildings must be able to withstand the force. When designing today's high-rise buildings, architects and engineers use wind tunnels extensively before they commit a structure to concrete and steel.
You really need to model the structure in a wind tunnel, actually model a scale version and see how it behaves before you really understand the loads you have to deal with and the accelerations that occupants will feel during windstorms.
Information collected from wind tunnel modeling has enabled designers to take a new approach to creating structures that can deflect wind more effectively. Moving beyond traditional square-cornered buildings, they can now design the corners of structures to have a more aerodynamic flow of wind around them.
You can round the corners of a building, you can chamfer or 45-degree cut the corners of the building back, or you can create little stair steps, little sawtooth corners.
New building designs can't come quickly enough because it seems the great storms are striking more frequently and ferociously than ever. Is global warming responsible for the recent super hurricanes? Pacific Ocean typhoons are often stronger than Atlantic hurricanes because they form over a larger ocean, which gives them more room to grow before they hit land. Nature Tech Hurricanes will return on Modern Marvels. We now return to Nature Tech Hurricanes on Modern Marvels. In 2005, the hurricanes Katrina, Rita, and Wilma all struck within a 30-day period. Each reached Class 5 status, with wind speeds more than 155 miles per hour. Some refer to storms of this intensity as supercanes. To many, it seems these giant storms are forming more often, and with greater strength than ever before. Some attribute this onslaught of hurricane activity to global warming. Each day, solar radiation hits the Earth's surface, warming the land and the sea. Some of this heat is radiated back into the atmosphere, where it's trapped by naturally occurring gases, like water vapor, methane, and carbon dioxide. This trapping of gases causes what is known as the greenhouse effect. For millions of years, like a good greenhouse, this system has kept the Earth's climate relatively stable. Yet during the last century, this global greenhouse has been warming up.
Many believe that this is being caused by human activity or anthropogenic activity, specifically the burning of fossil fuels such as coal, gasoline, heating oil, natural gas. They produce carbon dioxide. We know for a fact that carbon dioxide levels in the atmosphere have been increasing over the last 100 years. And it's believed by many that this is causing the Earth to warm up.
This change in the Earth's atmosphere may have an effect on hurricanes.
The important thing for hurricanes is general warming of the globe. Pretty good evidence that the world's oceans in general are getting warmer.
Warm oceans indeed affect hurricane conditions. But prudent scientists warn that the hurricane equation is much too complicated to be understood in terms of global warming alone. Weather records kept for decades reveal a frustrating inconsistency in storm trends. Yet despite this inconsistency, scientists now feel they've found a long-term pattern of hurricane activity. They call it interdecadal frequency.
Interdecadal frequency refers to an oscillation or variation in the number of hurricanes. You'd find periods on the order of 10 or so years where you'd find a decreased number of hurricane occurrences, and then over another period of 10 or more years, you'd find an increase. Many hurricane forecasters believe that we are now in a period where we are in an upswing in the interdecadal frequencies, and then presumably they believe that after a period of 10 or more years the frequency would drop off again.
Back in the 1930s up until 1969, we had a lot of hurricanes in the Atlantic, Caribbean, and Gulf of Mexico. From 1970 until 1995, there was a real lull. Beginning in 1995, we've had a lot of hurricanes.
But this oscillation doesn't seem to depend on global warming.
For complicated reasons involving ocean currents, the water of the Atlantic Ocean tends to get warmer and cooler over 20 or 30-year periods. These cycles seem to be completely natural. Now, global warming could be imposed on top of that, but the basic cycle seems to be just part of the way the world works.
When you analyze this over the 50-year period, there's no clear indication that the number is either increasing or decreasing. In fact, it appears that it may be remaining the same.
Although the number of hurricanes being produced may not be attributed to global warming, some believe their intensity has grown dramatically because of it.
It's not definitive, but in principle, if global warming is causing increased sea surface temperatures, and there is some evidence that sea surface temperatures have increased, it is entirely possible that this would result in more severe hurricanes. The number of severe hurricanes, categories 3, 4, and 5, is double what it was about 15 or 20 years ago. And, this raises some questions. On the other hand, when you listen to the people who've been forecasting hurricanes, they believe that this is just part of this interdecadal oscillation, and perhaps in past years there were a lot of severe hurricanes that we didn't know about because they didn't strike populated areas.
So the verdict is still out on the effect of global warming on hurricanes.
Is global warming causing increased sea surface temperatures which are producing this, or is there some other phenomenon out there that's producing it that we don't understand yet? As time goes on, depending on the kind of correlations that we see, then we should know.
Hurricane frequency and intensity are just two of the mysteries some scientists are exploring. Others are studying how to stop the deadly storms altogether. But is our current technology capable of stopping the most powerful storms on Earth? Ships have survived hurricanes by sailing fast enough to stay inside the eye. When this happens, flocks of seagulls often land on the ships and ride out the storm with them. Nature Tech, Hurricanes, will return on Modern Marvels. We now return to Nature Tech, Hurricanes, on Modern Marvels. Technology is helping us to better understand hurricanes. But can it answer the fundamental question? How do we stop them? In 1962, after several major hurricanes ravaged the East Coast, an ambitious project was launched called Storm Fury.
The Weather Bureau, which became the National Weather Service, the Navy, various people were involved. Project Storm Fury from the early 1960s until 1982. And they had some hypotheses, some ideas of things you could do to weaken a hurricane.
The project involved seeding clouds with ice-forming substances, like silver iodide, which would hopefully disrupt the storm's eye wall and cause it to collapse, thus reducing the winds. When first implemented, the results were encouraging.
The Storm Fury experimenters attacked 4 hurricanes on 2 occasions each, so a total of 8 trials. 4 of the 8 tries to weaken a hurricane, the hurricane weakened. This was particularly true of Hurricane Debbie in 1969, where it weakened both times they hit it, and they thought they were making hurricanes weaken.
But then scientists learned as they studied hurricanes more, flew airplanes into hurricanes more and more, that storms naturally go through a cycle of growing stronger and weaker. And so nobody really knows that what the cloud seeding make Debbie get weaker, or was Debbie going to get weaker anyway?
In addition to the inconclusive findings, the project faced some potential political problems because it might be altering the natural course of the weather.
The government said, you know, if we were to seed a hurricane and it were to trash Miami or Atlanta or Havana or any coastal city, regardless of what the seeding had done, we would look real bad.
And essentially after 20 years of some really, really smart scientists trying to find a way to weaken a hurricane, not to make it go away, they decided that it just really can't be done reliably.
But Project Storm Fury was far from a failure. Its contribution to hurricane science was pivotal in helping us understand the nature of the storms.
In fact, the one thing that came out of the Storm Fury project, scientists learned a lot about hurricanes. It focused them. They had to really learn how hurricanes work.
Hurricane scientists continue to propose other ways to weaken the storms. While they each have their merits, they also pose their own problems. One proposal involves towing icebergs into the path of a forming hurricane to lower the water temperature.
There are a couple of problems, principally that it would take an awful lot of icebergs. Towing icebergs to put them in front of a particular hurricane isn't real practical because towing big objects across the ocean is really slow. If you tow a oil drilling platform, the tow moves at 1 or 2 nautical miles an hour, whereas a hurricane moves at 10 or 15 or 20 miles an hour. So getting the iceberg and the hurricane in the same place would be kind of tricky.
Another proposal involves covering the ocean with a chemical film.
There is one technique that would work. That's to spread a soap-like film on the ocean surface that would slow down evaporation and deprive the hurricane of its energy. It would have to keep on working as the hurricane came through, and of course it'd have to be environmentally benign. Nobody's found a substance that fits the bill. If somebody does, it would probably be worth trying. But so far, we don't have any chemical that shows any promise. The substances that have been tried basically break up when the wind blows 10 or 15 miles an hour.
So it seems for now, Mother Nature has won the battle. And some wonder whether we should really be fighting her at all.
Then there's a question, do you really want to try and control something like this? In other words, this is a natural occurrence that exists to take the buildup of energy near the equator, because that's where we get the most intense solar radiation flux, and dissipate that energy toward the poles. So these hurricanes fill a needed purpose in maintaining our planetary energy budget.
A much better way to spend your money is build buildings that stand up, figure out where you really should have them, improve evacuation, improve forecasting. But as for doing something to a hurricane, no. You're better off preparing for the hurricane.
One thing is certain. Hurricanes aren't going away. It's only a matter of time before the next one hits. How prepared we are and how knowledgeable we are about this deadly force of nature will temper the toll it takes on our structures and our society.